Hello and welcome to a digital lecture for Calculus 2 at Salt Lake Community College. In this video we're going to go through section 6.3. To start off with, what we're going to do actually is an example of finding the region using what we already know from 6.2. And what we're going to try to show is that there are some problems with some reasoning behind that, with either using disks or washers. We have here, rotate the region bounded by y equals 1 over root x, the x-axis, x equals 1 and x equals 4, about the x-axis, and then we're also going to do that with the y-axis. So we're going to rotate around both of them, or we're going to try to anyway. First, let's graph this. The only complicated one is 1 over root x. That acts just like 1 over x, it just goes down slower. And we know 1 over x looks something like this. Where it approaches the x-axis, and technically it goes up to infinity here. But here, if we have the x-axis, which is just here, we have x equals 1, and we have x equals 4. We have this region right here. Now what we're first going to do is rotate that around the x-axis. So that means we're going to make a vertical slice like this, and then we're going to take that slice and we're going to rotate around the x-axis. That way we get a little picture that looks something like that. Okay, so that's kind of what we're trying to create, this little platform kind of shape. Well, we should be able to do that. That one shouldn't be too complicated. To do so, we'll do volume equals pi, because we're going to do pi r squared, of from 1 to 4, since we're using the x-axis, and then we're going to plug in our value of 1 over root x squared dx. Nice and easy. Okay, well, we have pi times 1 over 4. If I square this, I just get 1 over x dx. And then if I take the integral of 1 over x, what I get, if you're not aware of this one, this is one to keep in mind. The integral of 1 over x is natural log of x. And this is going to be from 1 to 4. Well, if I plug in 4 into natural log, I'll just get natural log of 4, which is some decimal. But if I plug in 1 into natural log of 1 equals 0. So that's just not even necessary. So I'll really just get an answer of pi times natural log of 4. Or whatever that is as a decimal. Now, that's doing the x-axis. That's nice and easy. Now, what if I didn't have any of that? What if I still had this stuff, but I was rotating this around the y-axis instead? That means I'd be making a slice like this, and I'd be rotating this around the y-axis, like so. So you can see that this is going to get a little more complicated because we'd be having an outside slice and an inner slice, so that means we would need to subtract the two. But even more so, that first cross-section that I created, that's going to define an outer slice that's using 1 over root x, or what would actually be 1 over y squared. But that's what this equation of the line is. However, when I have a cross-section that's later on, like here, this is no longer defining an outer slice of 1 over root x. This is now defining an outer slice of x equals 4. Therefore, that means that at this point right here, at that point, I need to create another integral. I need to create one integral where the outer slice goes to my original equation, and the second integral where the outer slice goes to x equals 4 instead. So that means we'd actually create two. I create one from, in this case, x equals 1 into here would go to 1. X equals 4 right here. That goes to 1 over 4 would be 1/2. Or 1 over root 4 would be 1/2. So from really 1/2 up to 1, I have the outer slice being 1 over root x. If I have y equals 1 over root x, that's the same thing as x equals 1 over y squared, if you do a little bit of algebra. So then I have the outer radius being 1 over y squared minus the inner radius of 1 of x equals 1 dy. And then I have to add another integral from 0 to 1/2 of an outer radius of x equals 4 minus an inner radius of x equals 1 dy. So that means I have two integrals I need to work with, which sucks. You really don't want to do this. It is possible in this case, but you can see how this is getting more and more complicated. There is a far easier way to approach these integrals than to split them into two different pieces. And that's what we're going to show in just a bit. All right, if we do solve for this, let's see if we can solve for this in this space. Doubt it, but we could try. 1 over y squared is 1 over y to the 4th, which is otherwise known as y to the negative 4. Which if I make that into an integral, or if I apply the integral to that, I'll get, oh, these all have pi, by the way, pi and pi. I'll get pi of, it'd be y to the negative 3rd, would increase it by 1, and 1 over negative 3. And then this is just 1, so that's minus y. And then for the other pieces, which is also multiplied by pi, but it's bounded on a different region, so I need to keep it separate. That's just 16 minus 1, which is otherwise known as 15, so that's 15y. Okay. Solving for those, if I plug in 1, I get just 1 here times negative 1/3, so negative 1/3 minus 1. And then if I plug in 1/2 into this, I get y to the negative 3 times, if I plug in 1/2 into that, I get 1 over 2 to the 3rd, or 1 over 8 times a negative 3. Wait, no, 1/2 into that would be 1 over 8, and then that would flip to the other side, so you get 8/3 negative. And if I plug in 1/2 here, I just get minus 1/2. And then plus pi, this one going from 0 to 1/2. The 0 doesn't even matter, I could just plug in 1/2 right now and call that one a day. That gives me 15/2. So pi times 15/2. Okay. Looks like I'm running out of room here, so let's just do a little bit of mental math. Negative 1/3 plus 8/3, that gives me 7/3. And we have a minus 1 and another plus 1/2, so that's really a minus 1/2. So 7/3 and minus 1/2, and we also have the 15/2. So minus 1/2 from 15/2 gives me 14/2, right? Yeah, 14/2, which is 7. So we have negative 7/3 plus 7. 7 times 3 is 21. That's actually a positive 7/3. So that's 21 plus another 7 gives me 28/3 times pi. Okay, 28/3 pi. Notice how long that took and how gross that is. There's another way of solving that, and that's what we're going to show here. So we have that another way to solve for the volume of solid is by using what is called method of cylindrical shells, or we'll just call it method of shells, usually. We can generate that by considering the original formula for the cylinder as the area of the base times the height. So we have, as if we try to generate this formula, or think about it, that's going to be the area of the base times the height. Well, we know how to find the area of the base of a cylinder. If I think about a cylinder like this, like so. If I try to make a cylindrical shell, that means that I don't have the full cylinder. I'm actually cutting out a piece of it. Cutting out this piece. And so when I'm trying to consider the area of the base, well, this looks like a washer to me. To find that, if I even look at the top of it, to find that, I need to find the area of the farther one and then subtract out the area of the closer one. Well, if I say the farther one has a distance of r2 just generally, and then the one on the inside has a distance of r1, then that means that this is going to be pi times r2 squared. That'd be the area of the outer radius, minus pi times r1 squared times the height. I can split that up. I can reduce pi out of it, but then I have r2 squared minus r1 squared. That's a difference of squares, which I can split up as r2 minus r1, actually plus r1, times r2 minus r1 times h. That would be what the difference of squares means. And then what I can also do is a little bit of a math trick. In this case, I can change this r2 plus r1 into something more familiar looking. Well, let's give me a little bit more room. I can change r sub 2 plus r sub 1 and introduce a division of 2. However, if I do that, I need to also introduce a multiplication of 2 somewhere. So let's put that on the outside. And then I have height, and I also have that r2 minus r1 bit. Well, what I recognize this as, the reason I introduced that division of 2 is because r2 plus r1 divided by 2, that's an average. That's how you find an average of two things. So, since that's an average of two radii, we can say that that average radius is just the radius in the middle of them, and I could just generally call that r. So we'll say 2 pi r, that's what this is. And then we have the height, and if I see r2 minus r1, that's the difference of the two radii, or how thick the shell is. That's something that we're used to. We're used to how thick each slice is, or each cross-section we create. So I can say this is delta R. That is the equation that we're looking for to try to generate the formula for the volume of a cylindrical shell. If I try to make a limit of this as the delta R, or how thick each cylindrical shell is, or if you want to say n of how many cylindrical shells I create, then I can create the limit of this as delta R goes to 0 or as n goes to infinity, and I can create the following formulas for volume. I create volume as the integral of 2 pi from a to b of x times f of x dx, or the integral of 2 pi from c to d of y times f of y dy. Here we have the 2 pi bit. R is either the x or the y. That's the radius, or how far along the axis that you're rotating you are. And then the height is just going to define the function. Delta R, that's our dx or dy, whichever one we're dealing with. So all of our pieces are in place. There's a couple benefits to this formula. If you notice, there's no squared anything. And that was kind of an annoying bit of 6.2, that you always have to square things, and sometimes that makes a really long polynomial that you have to work with, or maybe something that's even worse to try to deal with. Like if you try to square natural log of x. We can deal with that, but it's problematic to do so. Here we don't have anything like that. We don't have any squares. We do have that we're multiplying x times whatever the function is, or we're multiplying y times whatever the function is. So we are going to increase the degree of the function at least by 1. But other than that, it is a little bit more simplistic to deal with. A couple things you are going to have to notice is that since the radius r is how far along or away from the x or y axis you are, which you're using y or x to represent that, you will need to adjust that if you are rotating around something other than the standard x or y axis. We had that before as well, where we needed to subtract appropriately inside of the radius before I squared it in order to adjust for rotating around a different axis. And the same is true here. However, we're not going to have to change much. We're really only going to have to change either x or y. So it'll usually be whatever axis we're rotating minus x, or whatever axis we're rotating away from x. And we're just going to have to separate that there, which means it's going to be a little bit more complicated to multiply out, but not terribly so. However, that also means that we don't need to change the height. So even if we're rotating around a different axis, that's not going to change the height of the shell you were creating. It would change the height before, but in this case, since it's the shell away from it and we're rotating just around a different axis, the height of the curve is still the same regardless. So we don't need to change f of x or f of y. We would need to do that, though, if we're finding like a difference of curves. So if we're finding a difference of curves, that's where f of x or f of y is just going to be a difference of 2, which we'll have an example of in a bit. Another really important thing to keep in mind, which is really helpful here, with the disks and washers, the variable that we had in the integral and the axis that we were rotating agreed. So if I was rotating around the x-axis, I was using x variables. If I was rotating around the y-axis, I used y variables. With cylindrical shells, it's the exact opposite. If you're rotating around the x-axis with cylindrical shells, then that means your function should be defined in y. If you're rotating around the y-axis with cylindrical shells, the function should be defined with x. And that's because all how we draw the shape. So it'll always be important to draw your shape and draw your cross-section to see how that slice should be defined. Okay, so let's go through a couple examples so you can see these in action. So the first example, example 1, is actually the revisited example 1 that we had from before. So we're going to redo this one around the y-axis, except we're going to make it a little bit simpler. If I recall, when we go back up, we saw that the volume we had was 28 pi over 3. So that's the answer we're going to try to find here again using cylindrical shells. Okay, so just a quick drawing. We have 1 over x. We drew that before. We knew 1 over x looks like this. And it was from 1 to 4, like so. And what we're rotating around is the y-axis. Now before, we did it with a washer. We did that making this slice and rotating around that way. However, in this case, if we do it with the shell, what we would create is a slice that looks like this, and then we would rotate this slice around the y-axis, creating a shape that looks kind of like this, with a hole in the middle, like so. All right, notice that we're rotating around the y-axis, so that means we're going to keep this in terms of x, so we're going to keep this as y equals 1 over root x. And we're bounded from 1 to 4. So if we set up our volume using cylindrical shells, we have 2 pi from 1 to 4 of x, since we're not rotating around a different axis, x times the function of x, which is 1 over root x, dx. Notice another really helpful thing here, even though there was a space in the middle of this, there's this empty part going through the middle, I don't need to account for that with the cylindrical shell, because the bounds from 1 to 4 will already take that into account, that I'm not taking that middle area. So that also makes it a little bit easier. Now, if I want to solve this, I have 2 pi from 1 to 4. X times 1 over root x would just be the square root of x, because that'd be square root of x squared over root x dx. So that equals 2 pi of root x, the integral of root x is 3/2, 2/3 rather, x to the 3/2, from 1 to 4. And then let's plug in 4 and 1. So 2 pi. If I plug in 4, I get 4 into 3/2 would be 2 to the 3rd, which is 8, times 2, which is 16, over 3. Minus, if I plug in 1, I get 1 times 2/3, which is 2/3. So I get 16/3 minus 2/3 is 14/3, times 2 pi is 28 pi over 3, which is the same answer we got before. So checks out. And notice how much less work that took. I'm not going to say that the volumes with cylindrical shells is preferential in every situation. Sometimes it has the same problems that shells do. it really depends on the case that you're working with. You really want to use shells in a few situations. If using the washers would result in using multiple integrals, if you have that, try using cylindrical shells instead. Or if isolating the variable is too difficult. So for example, if I had y equals x squared plus 3x minus 2, and I wanted to rotate this around the y-axis, I wouldn't want to do that with a washer or a disk, because that would involve trying to get this to be x equals something, which is hard to do when an x shows up multiple times. So if it's really difficult to try to isolate a variable, then maybe consider using a different method. All right, let's do the next example. Rotate the region in the first quadrant that is above y equals x squared and below y equals 2 minus x squared about the y-axis. Okay, so first quadrant, above y equals x squared, and below y equals 2 minus x squared around the y-axis. Okay, y equals x squared, that's the parabola, and 2 minus x squared is the parabola that's going down and starts at y equals 2. So that looks like this. That would be y equals x squared. And 2 minus x squared would start at 2 and would curve down this way, and that would be y equals 2 minus x squared. And they intersect at some point. And actually, I should draw this better because they do intersect at a very easy to recognize point. They should intersect, there we go, it's a little bit better. They should intersect at 1 right there. You can even solve for them. You can put them equal to each other if you want to solve where they hit each other. And we actually do need to do that because we do need to solve for where they hit each other on the x-axis. The y-axis is easy. But I want to put them equal to each other, so I say x squared equals 2 minus x squared. Add x squared to the other side, I get 2x squared equals 2. Divided by 2, I get x squared equals 1. So that means they hit at plus and minus 1. So 1 here, and also would hit on the other side of the y-axis. But we only care about the first quadrant, so we're bounded by this region. Okay, now in this case, this is one that is definitely better to do with cylindrical shells. Why? Well, if I was rotating around the y-axis and I did this with washers or disks, then I would use a disk that looks like this, and I would rotate that around. The problem with that is that once I reach that point of intersection, the cylindrical disk, or the disk itself, will have a different function that defines its outer shell, or the outer part of it. So that means I would have to set up 2 integrals. But, well, erased a little bit too much there. Okay. But if I use cylindrical shells instead, like so, then that means at all points, the top curve is always the same and the bottom curve is always the same. So it's consistent. That means I should only need to set up 1 integral to solve for this. So a lot easier to do compared to doing disks instead. All right, so let's solve for this. We have volume equals 2 pi. In this case, we're rotating around the y-axis, so that means if we're using shells, we're going to use x variables. We're going to keep them as they are. We don't need to solve for y. And that also means that the bounds we use are from 0 up to 1. So 0 to 1. The radius is x, it's how far along we are, but the function we have is going to be a difference between the top curve and the bottom curve. The top curve is defined as 2 minus x squared, and the bottom curve is defined by x squared. So I subtract those two, dx. Therefore, we get 2 pi from 0 to 1 of x times 2 is 2x. That's a minus x squared, so minus 2x squared times another x gives me minus 2x cubed dx. And I can even pull out a 2 there if I want to. So I'll say 4 pi. If I pull out the 2, that'll give me, let's actually keep the 2 in there for this reason right now. If I do 2 pi, 2x integral will give me x squared straight up. And then minus 2x cubed will give me minus 1/2 x to the 4th. This is from 0 to 1. 0 is nice because it's going to cancel that part out, so I don't need to worry about it. All I need to do is plug in 1, so I get 1 minus 1/2, which is otherwise known as 1/2, and therefore we get an answer of pi. So my entire solution is pi. Okay, so that's example 2. We have a few more to do before we can call this section done. Number 3, rotate the region bounded by x equals y squared, y equals 2, x equals 0, about y equals 2. All right, well, x equals y squared, that's a parabola starting at x going up the x-axis. Y equals 2, x equals 0, about y equals 2, so that means we're in the first quadrant and we're rotating around a different axis. So x equals y squared looks like this. Let's make that a little bit better. Have a little more room. So x equals y squared looks like this. Y equals 2. 1, 2, why not? I'll say that that's y equals 2. So it's bounded by y equals 2, and x equals 0 is the y-axis. So that means we're looking at this shape here. I'll highlight in blue. We're looking at that shape there. And we're rotating that around y equals 2. Now if I do that with cylindrical shells, I would have a cross-section that looks like this. And we'd be rotating that around this curve right here, around y equals 2. So that'll give me a little bit of a pyramid shape if I make this. So yeah, a cone shape more or less. Okay, so since we're making that cone, we can solve for this. We can say, all right, well, that's volume equals 2 pi. In this case, we're rotating around something similar to the x-axis, so we should be using y-coordinates. So we should be using 0 to 2. And we're using y-coordinates, so we're going to keep that function as y as well. I'm going to keep the radius separate for now. The function is just y squared. And then we have dy. The radius is a little bit tricky. The radius is not going to be the same because we're not rotating around the same axis. The radius is how far away from the axis we are at any given point. So if I treat this y equals 2 as the original x-axis, I'm considering how far away we are. Well, that's considering if I'm going from how far away we are from 2, that's a distance of 2 minus however up we are in the y direction. So that means that this is going to be a radius of 2 minus y. That's how far away we are from the axis of y equals 2. So we can multiply those out pretty nicely. 2 minus y distributed with y squared, I get 2y squared minus y cubed dy. And that's a nice polynomial, pretty easy to integrate. 2y squared will give me 2/3 y cubed, and y cubed will give me 1/4 y to the 4th from 0 to 2. Solving for that, don't need to worry about 0, just need to worry about 2. 2 into y cubed will give me 8 times 2 gives me 16 over 3. 2 into y 4th also gives me 16, divided by 4 gives me 4. So we get 2 pi times 4 over, if I put that over 3, that's 12/3. So 16/3 minus 12/3 is 4/3. And we get an answer of 8 pi over 3. Okay. Now I will say you can also do this. If you notice, this one didn't have any problem with doing it with disks instead. If you wanted to integrate this question using disks and rotate that disk around, that will work perfectly fine. There is no problem with doing that. The only difference at that point is that you need to notice that the function that you're integrating on is actually now 2 minus root x. That's the function you would need to use as the radius if you were to do this as disks instead. That should give you the same answer, though, of 8 pi over 3. I think that one would take a lot more work because then you would need to square this one, and you have a lot of roots thrown around. This one we did with just a simple polynomial, a little bit easier. All right, example 4. Rotate the region bounded by y equals 3 plus 2x minus x squared around x equals 4. All right, 3 plus 2x minus x squared. That is a quadratic that I should be able to split up pretty nicely. Let's do that. That should be, okay, so negative x squared, so I have negative x and x. 3 can only be multiplied by 3 and 1, and because I have 2 in the middle, then that means that the 3 was the positive one, so it should be linked right here. So plus 3 and the x should multiply to make a positive 3x. And then a plus 1 over here should multiply to make negative x plus 1, should be minus x to give everything I need. So that should be another way of representing that, which means that that is a parabola which intersects at 3 and negative 1. And it goes down because it was a negative x squared. So it looks something like that. Okay, now we have that, and we're rotating it around x equals 4. So we're rotating around this axis right here. Okay, this one I definitely want to rotate around the axis x equals 4 using cylindrical shells. Also, to make this simpler, let's just make this let's make this in the first quadrant. So we'll just make it from 0 to 4, just make it a little bit easier. So we'll say this in first quadrant. But it says region bounded by that, probably first quadrant, but it could also mean up to or over to negative 1. But 0 to 4 should be fine. The reason I want to do this with cylindrical shells, however, is because if I try to make a slice like this and rotate that around, that would be a cylindrical shell, then that means that throughout the entire function, or through the entire time from 0 to 4, the top part of the curve is always the same. It's defined by the function y equals 3 plus 2x minus x squared. However, if I were to try to do this with a disk like this instead, it would be fine for a while up to this point, but then after that, I would have a disk like this, which is defined from the function to itself. That's problematic. You also don't want to have that happen, where you go from one function to itself. So that's kind of bad. We're just going to use a cylindrical shell to solve for this. Okay. So we have volume equals 2 pi times the integral from 0 to 4. We're integrating the, or not 0 to 4, we're integrating the function from 0 to 3, rather. And then we have a radius. The radius is going to be defined as the distance from the rotation axis, which is x equals 4, over to the curve, so right here, which has a distance of 4 minus x. So 4 minus x as a radius, and we multiply that by the function, which is 3 plus 2x minus x squared dx. Now that one's a little more gross, because that one involves a little bit more foiling, but not too bad. 4 times 3 gives me 12. 4 times 2x gives me 8x. 4 times negative x squared gives me minus 4x squared. And then we multiply the minus x, so we get minus 3x minus 2x squared, and then minus, or actually plus, x cubed dx. Or if I simplify that, at least as much as I can, I get 12 as my only constant, 8x and 3x, so I get 5x. We get minus 4x and minus 2x squared, so we get minus 6x squared, and then plus x cubed dx. Okay, so that's what we would solve, and this one is a pretty general polynomial, so you can solve that at this point. Again, from 0 to 3, solve that as a polynomial. Notice that the bottom is 0, so you don't even need to worry about that, and you can find the solution for that function. So I'll leave that to you. Last one, for example 5, we have the same region, and again, I'm only going to consider it in the first quadrant, so from 0 to 3. And in this case, we're going to rotate it around y equals -1. So if I have the same function, so from -1 up to 3 is where it intersects, like that. What we're going to try to do is we're going to rotate that around y equals -1. So we're going to rotate it around this axis. In that case, if I wanted to do cylindrical shells, then I would do a shell like this, and I would rotate it around that way, which would be problematic for the reason I was stating earlier. I would then get a shell that looks like this, which goes from the function to itself. That is bad. We want to avoid that. What we're instead going to do, this one is going to be a washer. A washer would prevent me from having any problems with that. I would really only have the difference of 2 radii when I rotate this around, because I'm going to create kind of a donut shape, or a washer shape, I guess. Okay, so not every question is going to be, oh yeah, this has to be a cylinder, or this has to be a washer. The main question is draw it, see how the discs could work, or how the cross sections could work, and try to figure out which one is preferential. Sometimes either of them could work. Usually one is better than the other. Okay, so since this is going to be a washer, that's going to be the volume equals pi r squared for each of them. However, we're going to have a difference of 2. So we have, in this case, since we're rotating around something similar to the x-axis, we're still using values for the x, so 0 to 3 still. Since we're only considering this region in Q1, or at least that's what I'm going to restrict this to. We have the far axis as 3 plus 2x minus x squared minus a -1 squared, plus, or actually minus, the inside, which is, in this case, 0 minus a -1 squared. Okay, and also dx. All right, so that'll give us pi from 0 to 3. This one is really 4 plus 2x minus x squared. And this one is just -1 dx. So if I simplify that out at least a bit, I get 16 plus 8x minus 4x squared. And then I get 2x times everything. So I get plus another 8x plus 4x squared minus 2x cubed, and then minus x squared times everything. So minus 4x squared minus 2x cubed, and then minus, or actually plus x to the 4th, and then minus 1 from here, dx. All right, kind of long. I can try to simplify that to make it at least a 4-term, 5-term maybe. I have constants of -1 and 16, so that's 15. I have 8x and 8x, so that's 16x. I think that's the only ones I have for a single x, and then for 2x's, I have minus 4x, and plus 4x, it looks like. Did I do those right? Yeah, it looks like. Okay. So that means those two will cancel out, so I have minus 4x squared. And then I have those for 3's, so I have minus 4x cubed plus x to the 4th dx. All right. And that going from 0 to 3. So a little bit gross, but again, that just comes out to another polynomial, which is easy enough to integrate on using the same processes we've been using constantly, and then you can get your solution from there. With that said, that's enough for section 6.3, going into how to do the volume using cylindrical shells. If you have any questions, feel free to put those into the comments below or ask your instructor directly. Just keep in mind that a lot of these questions are pretty flexible, and you should be able to do a lot of them in multiple ways. So that's kind of the benefit of calculus. It's whatever you see first, and you can try. And even if you see the complicated way, there's usually a way around it or a way to do it. But with that said, that's everything that we have. So I hope you have a nice day.